Good evening, all. So, as a part of online series lectures, let's discuss on fundamentals of cryptography. So, generally, whenever we start understanding cryptography, we should get familiar with different terminologies, as you can see over here. So we will start with the most two important terminologies. One is the plain text and another is the ciphertext. Perhaps the backbone of any cryptographic process, because as we know that cryptography is a process of converting plain text into an equivalent ciphertext, which is also known as the coded message. And there are some other very important terminologies in this particular scenario we should adapt. Just like, as I told you, key, a very important component, perhaps one of the driving force in bringing complexity while we are converting the plain text into a corresponding ciphertext. So we will learn about key in detail. At the same point of time, we should also know two very important strategy, like say, for example, one is known as encipher, or sometimes it is also known as encryption. Whenever you are converting a plain text to a scrambled text or a type of cybertext. At the same point of time, the reverse process is generally known as the process of decryption, is also known as decipher, whenever you're converting any specific ciphertext back to a plain text. Generally, the people who are getting involved with this particular process of cryptography, and at the same point of time, they start understanding that what are the best possible way of breaking a ciphertext into a corresponding plain text is known as the crypt analyst. And that's also known as the process of crypt analysis, to figure out, to validate how strong a cryptographic process is. And at the same point of time, cryptology is one of the field where generally we talk about the cryptography and crypt analysis. So certain terminologies we got familiar with. Let's start understanding the language of cryptography. So in this particular slide, you can observe that we are making use of an encryption algorithm over here to convert the plain text into a corresponding ciphertext. And followed by that, using another specific algorithm that is known as a decryption algorithm to convert back the ciphertext into a plain text. So that's actually the process of cryptography, a basic framework of cryptography. And as we have seen that we are taking care of two specific key. One is Ka, given by Elias, who is the sender over here, and another one is Kb, the decryption key, which is used by the receiver, that's Bob in this particular picture. And unfortunately, you might have seen that the medium of communication is not at all a trusted medium of communication. So any specific intruder can start intercepting the message whenever we are converting the plain text into a ciphertext and transmit it towards the corresponding receiver. So in this particular stage, few things always we have to keep in mind, that what exactly is the nature of my key. And based on that, we have several concepts in cryptography, like say, for example, the symmetric key cryptography, asymmetric key cryptography, and at the same point of time, the most useful is the public key crypto system, which we will learning towards a later stage. So this is generally a very basic framework representing a fundamental workflow associated with a crypto system. So coming to the most important part, where generally we make use of identical keys for encipher and decipher, that's basically known as asymmetric key cryptography, or it's sometimes known as asymmetric key encryption. And this is obviously a very classical strategy when cryptography has been invented. So we start working on the concept of symmetric key encryption system. So as you can see that prior to 1970, uh, then it was one of the pioneer technology generally being used for incorporating sufficient level of safety and security whenever we transmit a message from sender towards a receiver. So if you see this particular diagram, the idea will be very clear. So we have a plain text. We are making use of a certain cryptographic algorithm. As you can see that we use the data encryption standard with a specific shared key between the sender and the receiver. The message got transmitted, and ultimately here we are making use of another algorithm which is just reverse to the encryption algorithm and getting the corresponding plain text. So this is generally known as a symmetric cipher model. And if you see this representation is quite simple, but the constraint is we are making use of an identical secret key which has been shared among sender as well as the receiver. At the same point of time, if you see this particular diagram, your idea will be more clear that when Bob and Eli start communicating with each other, so ultimately they're making use of the same key, like KA of B, and this is how the process is working. Finally, it's giving us the corresponding ciphertext, and we are making use of the identical key. See, in both sender and receiver side, the key remains same. And finally, we got the particular message back again in the plain text. So this is what exactly is the process of symmetric key cryptography, where we make use of identical key for both encryption as well as for the decryption. Now, the most important thing here to understand that what are the technical and functional requirements whenever you're talking about any symmetric key crypto system. So generally, very strong encryption algorithm, perhaps data encryption standard, advanced encryption standard, and we should make use of a standard secret key, which is common to both sender as well as the receiver. So this is one of the way through which we can implement the concept of symmetric key cryptography. Few things always we have to keep in mind while talking about any specific type of cryptography system, or if you are using it for an enterprise environment, certain parameters to be very, very important, like what type of cryptographic operation. Say, for example, the encryption operations we are going to use, whether it's substitution or it's transposition, or it can be a product of both substitution as well as the transposition. So we'll be having a discussion in the latter stage regarding this particular concept. Followed by that, what exactly is the nature of my key? This really, really important, perhaps the backbone of any cryptographic process. And at the same point of time, how a particular plain text is getting processed. It can be done using a chunk of code. Sometimes it's known as a block, or it can be done with the help of a stream of plain text. So these are certain parameters which are quite important while we are talking about the complexity or the efficiency of any cryptographic system. At the same point of time, few things are very, very important over here to understand in a real world application. Number one, there should be an unconditional security. And at the same point of time, there should be a computational security at the same point of time. Because we cannot have an assumptions how is the outside environment whenever you start implementing the idea of cryptography for an enterprise environment. So that's the reason these are two very important strategy always we have to keep in mind while we start developing a cryptographic environment. Few very important example we are interested to learn, like say, for example, the substitution strategy. What type of substitution technique we can make use whenever we start converting a plain text into a corresponding ciphertext. So we can use different type of pattern, different strategies while converting a plain text into a ciphertext. It can be done with using an alphabet in any specific language, or it can be done by using certain numbers. isn't it? And that's what exactly the process of substitution cipher. Let's take certain example of substitution cipher. The most ancient one is basically known as the Caesar cipher. And as you have seen in this particular example, that one specific alphabet M is getting replaced by the third letter that's known as the P. So this is basically a process which is followed in the ancient time, and that's why the name is Caesar cipher. It was invented in the period, in the era of Julius Caesar, and this is one of the simplest example of substitution cipher. If you see this particular example, it's a little bit more advanced where we can make use of the number theory of mathematics, and we can also perform a kind of substitution. Just like here, you have seen that we have taken all alphabet from A to Z, and they are represented using a specific number which is in a chronological sequence starting from 0 to 25. And based on that, we can make use of certain formulas as given over here to perform the encryption and decryption respectively. At the same point of time, whenever we start making use of cryptanalysis as discussed earlier, which actually validate the performance, the strength of any cryptographic process, through that we can understand that whenever you are making use of any specific substitution cipher, sometimes it's easily breakable. Anyone can guess what exactly is the pattern of converting the plain text into a corresponding ciphertext. Just like what we have already discussed about symmetric key encryption system, where generally we make use of an identical key, and ultimately we take a plain text, convert it into a corresponding ciphertext, and again using the same decryption key, we can get the plain text back. So that's what exactly is the process of symmetric key cryptography, where very efficiently we can make use of the technique we have learned so far. That's known as the process of substitution. So generally, there are different strategies being utilized whenever we are making use of any specific cipher. Like say, for example, monoalphabetic cipher is one of the most common example where generally we start finding out that what exactly is the frequency of using an alphabet. That's just by using a statistical process. And based on that, we can start guessing the appearance in a specific word. So this is generally done using a permutation strategy. So that's, we call it as a mono-alphabetic cipher. So whenever we are talking about any cryptographic process, so as a cryptanalyst, always we need to understand what could be the possible attacks can be launched in a specific cryptographic process. Just for example, as you can get over here, that sometimes the attackers would like to understand the pattern through which an algorithm can be explored, and that will actually can be launched in a specific cryptographic process to find out that what exactly is the probable plaintext by using certain trial and error method, and we can figure out the pattern in certain context. At the same point of time, if you see this particular table, you can understand that what exactly is the key size. And as per the key size, if you have a look on the time, so the time is actually increased as per the increase of the key size. And obviously, that's what is expected in any cryptographic process, to make use of a key as complex as possible in terms of size, in terms of different combinations, so that ultimately it takes an ample of time, maybe sometimes 6 years, even a decade, to get back the corresponding plain text, because that's what exactly we call it as a brute force search, where we can make use of trial and error to find out what exactly is my plain text just by going through the pattern of conversion from ciphertext to a corresponding plain text. Few very important attack. Let's have a look over here. Like as we have seen here, automated Turing machine. This is my financial organization, and what type of attacks generally launched in a specific system, because this is very important for an information security analyst to know the pattern of the attack before we start selecting a cryptographic process. So here, if you can see that a person who start changing the pin according to his or her choice, and finally this particular pin has been encrypted and transmitted to a specific bank. And finally, if you see that the medium of communication was not that much secure and it has been eavesdropped and finally being intercepted by an intruder at the same point of time. So this is one very simple way of launching a plain text attack in a very secure communication. As you can see, transactions between the automatic tellering machine and the financial organization. So this is one of the most important scenario which we cannot overlook, and we need to understand what type of cryptographic process can be applied over here to make the process much more complex to avoid such a type of attack. So as we have discussed that in any specific symmetric key crypto system, the most important thing which we need to understand over here is the encryption algorithm as well as the corresponding decryption algorithm. And this is the main role of any crypt analyst to find out the desired pattern. And at the same point of time, to make the communication more secure, so scientists have started developing a secure channel through that the data can be communicated. And obviously this data is a encrypted data which is getting transmitted using a secure channel so that we can avoid a strategy of eavesdropping or an intruder failed to intercept the message whenever it is in transit between source towards a destination. Another very important strategy we make use over here that's generally known as a polyalphabetic encryption. Earlier, we studied about the monoalphabetic encryption. So here, generally, we make use of polyalphabetic cipher, combining our concept of the Caesar cipher. And whenever we start combining two cipher technique, the process is little bit complex, advanced, which should be used for any specific type of cryptographic system. So we can generate different patterns also combining two or more cryptographic strategy and make a resultant strategy which can be applicable to any encryption process. Like substitution, there is another very important strategy we make use that's known as the process of transposition. So here, generally, we start rearranging the letter order and we don't alter the actual letters in this particular process. And this is generally known as transposition or a permutation process. Have a look on this particular example. So what we did, we have arranged it in a diagonal manner, this particular text, and simple plain text has been converted into an equivalent ciphertext. We didn't change any of the letter, but we have only changed the location. We have changed the location of every alphabet, and this is how we are giving a corresponding ciphertext. This is generally known as rel-fence cipher strategy, as we can see over here. So another very interesting process generally we use that's basically known as row transposition cipher. So you can see over here, we have made use of a specific key. And finally, as per the sequence of the key, we start arranging this particular letter, the sequence of the letter, and which is giving rise to the corresponding ciphertext. So we are starting with key position 1, then we are moving into key position 2, and so on like that. So a specific plain text can also be converted into ciphertext by reordering the corresponding columns. So that's one of the process generally we use in row transposition ciphers. Coming to the product cipher, which is actually a combination of substitution and the permutation concept. So if you combine both substitution and transposition or permutation, ultimately we're going to get a cipher strategy, which is known as the product cipher strategy at the same point of time. And a very interesting idea which is used in a financial organization that's basically known as a one-time pad, where we are using a specific key which is not getting repeated in any specific transactions. An unique key being used while we are performing any specific type of financial transaction. So that's the idea behind one-time pad. And this idea is really useful nowadays, even in generating a one-time password while we are making any specific type of banking transactions. A good way of increasing the strength of any cryptographic process, validating users with the merchant at the same point of time. There are several advantages of the one-time pad, as we know that here we are using a unique key for every transactions, and the key has been actually complexly computed using various mathematical and logical functions, and it's really difficult for an attacker to figure out that particular key. So that's one of the advantage. At the same point of time, there are certain disadvantages of one-time pad, as it doesn't talk about the integrity of any message which is in transit. And at the same point of time, an attacker can also figure out the pattern of generating the one-time key whenever a transaction is taking place. So that's why we came with certain modern approach that's generally known as a block. So instead of taking a specific plain text, now we are taking a chunk of plain text and we start applying a cryptographic process over here, just like we are going to learn DES, that's known as the data encryption standard, which works using the strategy of block ciphers. At the same point of time, we can also make a stream of data and convert it into a corresponding ciphertext. That process is generally known as the stream ciphers. So as per the requirement in any cryptographic system, we can make use of block ciphers or stream ciphers. So when we are talking about the block cipher, as I already told you, that here the computational process is really complex. Like say, for example, in data encryption standard or in advanced encryption standard, we generally make use of certain block cipher strategies, which is really difficult to break, or finding out the required pattern for getting the plain text from a corresponding ciphertext. Or even if we can break it, it takes maybe more than 2 decades of time to get the plain text back from a specific ciphertext. So that's what exactly is the strength of using a block cipher instead of using a plain text and converting it into a corresponding ciphertext. The process of permutation is quite interesting, as we have already learned. This is what exactly we do for the permutation, just rearranging the letter in different positions. Ultimately, we're not altering the plain text and applying the strategy of permutation to convert a specific plain text into a corresponding ciphertext. The same idea can also be used for generating different type of keys at the same point. Have a look on this particular process, which is generally the backend workflow of any specific block cipher. Just like we have seen that there are several blocks associated with the plain text, and we can make use of a specific key over here. And ultimately, key is integrated in every row of that particular block. Exactly the same concept we use in data encryption standard process. And if you see the workflow, that at every point we make use of a key, rather we can say a sub key which is generated from a specific key, and ultimately we make use of it whenever we start applying the concept of permutation, and sometimes it's also known as an Xbox permutation. Two interesting concepts we make use, which we will learning in a later stage. One is basically known as the confusion, another one is known as the diffusion, which is actually the backbone of any powerful cryptographic system. So ultimately, if you see that this workflow of this process, so in every phase, in every row of the corresponding block of plain text, we are making use of the key. We are repeating every steps as much as possible. Like say, for example, for data encryption standard, we make use of total 16 cycle to get a plain text and convert the plain text into a corresponding ciphertext. And ultimately, we can generate a corresponding block of ciphertext from a specific plain text. So this is what exactly we call an internal operation, which is associated with a specific block cipher. In a very simplified, abstract way, this is how we can represent a block cipher strategy. So I believe this particular process is quite interesting. At the same point of time, it's quite powerful also, which actually helps us to enhance confusion and diffusion to make the process more improved so that it's really difficult for an attacker to get the corresponding plain text back. So there are various principles generally we use, like as we can see over here, that we generally make use of different blocks. That's a chunk of data, and we make use of improved and advanced substitution strategies over there. And more or less, generally, we make use of both substitution and permutation whenever we are working with any specific block ciphers. The example which you're getting over here is Claude Shannon strategies of product cipher, which is invented in the year 1949. And as I told you, here we make use of two specific process. One is known as the process of substitution, also known as S-box, and the process of permutation, which is known as P-box. So both S-box and P-box can be integrated in one of this particular strategy, which has been invented by Claude Shannon in 1949. And have a look on the diagrammatic representation over here. So we have several S boxes. And finally, you can see that how we are using the permutation by rearranging the alphabet from one specific S box to a next specific X box. See the diagram on the right hand side where we are using a P box and a simple permutation strategy, that's rearranging of letter. The letter in position 1, you see it becomes a new position whenever we are making a specific transposition. So here generally we use certain exclusive permutation function which is accountable for implementing the idea behind P-box. And combining this both S-box and P-box, it makes the process more strengthened and helps us to give a block cipher in a much more efficient manner. As I was talking about these two most important terminology, that's known as the confusion and diffusion. So whenever we start dissipating the statistical structure of the plain text over the ciphertext, that's basically known as the strategy of diffusion. And whenever we start making the relationship between the text and the corresponding key as complex as possible, and that's basically known as the process of confusion. So that's why these two terminologies are very important in cryptography. Whenever we start making use of any particular crypto system, we always try to enhance the diffusion and confusion parameter so that it will be really tough for an attacker to get the plain text back. Coming to the most important cryptographic strategy which we use in real world, one is known as the private key crypto system, where the key has been shared by both sender and receiver. It's also known as the symmetric key cryptographic process. And at the same point of time, we also make use of a public key crypto system, the most popular one, where generally we make use of one particular public key and another private key. And this is also known as an asymmetric key crypto system because here we are not going to use an identical key for sender and receiver. Okay, so this is obviously a right strategy in today's world to perform any specific type of private communication between a sender and receiver, make use of the public key cryptographic system. And as I already told you that a public key generally it's known to anybody and can be used for the encryption purpose, whereas we can make use of a private key which is only known to the recipient and can be used for decrypting a specific message. So that's the basic idea behind the public key crypto system. And have a look on this particular diagram, your idea will be more clear that how generally we can make use of a specific environment where we are using an encryption algorithm. And as you can see, RSA is one of the standard algorithms generally used for public key crypto system. And as you can see in this particular diagram, Bob, which is having different type of keys. And at the same point of time, we are making use of the public key, which is known to both Bob and Alice. And thus we can use a cryptographic algorithm and the message has been already converted into a ciphertext. It's getting transmitted over here. And here we can make use of a decryption algorithm. And generally, we make use of the private key over here to get the plain text back. So this is generally the process of public key crypto system, a basic architecture of a public key crypto system where we are using an asymmetric key cryptographic system and making use of two different key. One is public, which is known to both sender and receiver, and which is used for making the encipher, that is converting a plain text into the ciphertext using any standard cryptographic algorithm. As I told you, RSA is one of the standard algorithm, and transmitting it to the receiver end. Receiver is making use of the private key to decrypt that particular message. So this is a very interesting as well as an efficient concept, which generally we use in the public key crypto system. So a few important characteristics always we need to understand whenever we are talking about a public key crypto system, that it's really difficult for anyone to find out the pattern until and unless knowing the decryption key. At the same point of time, it's more scientific and it's computationally more convenient to make a calculation whenever you know both the public and the private key. So it's very important to understand any specific public key crypto systems, what type of algorithm has been used in a specific public key crypto system, and how generally the system has been designed both in the source as well as in the destination. If you see over here, we have a message. So ultimately, we're using an encryption algorithm over here and making use of this particular key pair, as you can see over here. And finally, after encryption, when it comes over here for the decryption, we are again making use of a specific key pair source. As you can see over here, we are using two specific key pair sources for performing the encryption and the corresponding decryption. So this is a very good example, as you can see over here, that how the plain text has been taken and what exactly is the role of the key pair source when we are performing a specific encryption. So 2 times we can perform an encryption over here with the two different keys. And finally, when it's passing to the destination, here also we are doing 2 times decryption and finally getting the plain text back. So that's all about our today's session. Thank you so much.